An energy source is a physical process that human civilization requires to survive. Over centuries, humanity has systematically mastered a progression of dense energy carriers, moving from harvested firewood to mined coal, extracted natural gas, and pumped crude oil. Combusting these fuels releases carbon dioxide into the atmosphere, directly driving the greenhouse effect and melting polar ice caps. Acknowledging these long-term environmental consequences has forced the global scientific community and heavy industry to aggressively deploy alternative energy sources. This animation maps the vast roster of alternative technologies being pursued. Engineers harness solar radiation, wind streams, hydropower, and geothermal heat, while exploring the outer limits of atmospheric electricity, osmotic diffusion, and gravitational storage. Each system carries distinct physical characteristics, but capturing a naturally abundant force is only a fraction of the challenge. The true macro engineering limit lies in taking these highly intermittent physical forces and successfully integrating them into a massive, rigid civilization built entirely on the expectation of constant, on-demand power. This chart maps out the current scale of solar generation. Photovoltaic power plants are actively operating in more than 80 countries, achieving an installed capacity of over 770 gigawatts. Yet this massive infrastructure currently supplies approximately 3% of global electricity production. That percentage is remarkably small, given the theoretical capacity of the technology. The raw amount of solar radiation reaching the Earth's surface in a single day holds enough potential energy to meet the entire planet's power demands for a full year. To capture more of that surface radiation, a new wave of nations, including Kazakhstan and Egypt, is building out massive infrastructure. In regions with limited land, like South Korea and Chile, engineers are deploying floating photovoltaic systems directly onto bodies of water. The water cools the panels, which increases their electrical efficiency, while the panels reduce regional water evaporation. But deploying these arrays on salt water introduces a rigid physical flaw. Splashing water leaves behind crystalline salt residue. The salt quickly accumulates, blocks incoming light, and drastically drops output, forcing operators into constant labor-intensive cleaning cycles. Surface contamination dictates where solar can physically exist. A massive initiative to construct sprawling solar farms across the Sahara Desert ultimately failed due to two insurmountable realities: the immense cost of transmitting power to Europe, and the constant abrasive coating of desert sand over sensitive control equipment. The physics underlying these modern panels trace back over a century. Ancient civilizations used mirrored lenses to focus sunlight, but the scientific breakthrough occurred in 1839, when 19-year-old French physicist Edmond Becquerel recorded electrical current generating in electrolytic cells exposed to light, the first observed photovoltaic effect. The mechanical explanation for Becquerel's observation arrived in 1905. Albert Einstein provided the theoretical foundation for the effect by introducing the concept of light quanta, later known as photons, earning him the 1921 Nobel Prize in Physics. Theory became hardware in 1954, when Bell Laboratories engineers built the first working silicon photovoltaic cell. With no atmospheric dust to block radiation, these early cells found their optimal environment powering the first artificial orbital satellites. Solar generation runs completely silently and emits zero carbon during operation. However, manufacturing these panels requires extensive mining of rare earth metals and the use of toxic chemicals. When these glass and silicon panels reach the end of their lifespan, the massive scale of their disposal presents a severe, unresolved waste challenge. Despite relying on an effectively limitless fuel source, solar electricity is strictly bound by earthly constraints. It shuts down entirely at night, and its surface arrays remain permanently vulnerable to the physical environments they occupy. Wind energy is a secondary manifestation of solar radiation. As the sun unevenly heats the Earth's surface, it creates severe pressure differentials in the atmosphere, driving violent kinetic movements of air masses. This oscilloscope graph displays the electrical journey inside a turbine. The spinning blades turn a generator, producing an unstable, chaotic alternating current. The internal system rectifies this chaotic wave into a flat line of direct current, and then an inverter forces it back into a perfectly uniform alternating current, locked exactly at the 50 Hz frequency required by European grids. Harnessing this kinetic force is currently driving rapid global infrastructure expansion. China leads the world in total installed capacity, developing a single onshore complex in Gansu planned to reach 20 gigawatts, alongside massive offshore coastal developments. Because wind requires specific geographic corridors, adoption varies wildly by location. European nations with favorable coastal geography rely heavily on turbines. In 2019, Denmark produced 48% of its national electricity from wind, followed by Ireland at 33% and Portugal at 27%. Converting atmospheric currents into mechanical work is one of our oldest engineering achievements, utilized by ancient Egyptian river vessels navigating the Nile and medieval European grain mills. The first documented attempt to turn wind into electricity occurred in late 19th century Scotland. Inventor James Blythe built a 9-meter rotor at his cottage and offered his surplus electricity to the local town. The local authorities rejected the offer, deeming the massive spinning structure completely unpromising. This animation demonstrates why modern turbines all share the exact same silhouette. 3 blades represent the physical optimum for energy extraction. Fewer blades fail to capture enough kinetic energy, while adding a 4th heavily increases aerodynamic drag without proportional power. Harvesting kinetic energy generates heavy mechanical friction. Turbines emit both audible noise and low-frequency infrasonic vibrations that physically impact living organisms, permanently restricting these massive structures from being built near residential population centers. Like solar technology, wind turbines tap into massive physical forces, but their reliance on specific meteorological corridors, combined with unpredictable output and heavy noise generation, structurally tethers them to highly specific, isolated geographic zones. In the sky above us, massive air mass movements and moisture evaporation in the atmosphere generate continuous, violent separation of electrical charges. The scale of this phenomenon is immense. The atmosphere holds a permanent positive electrical charge. The total energy potential of this electric field is estimated at 10 million gigawatts, a figure exceeding the entire power demand of human civilization by over 250 times. Scientists have tried to intercept this atmospheric charge for centuries, beginning with Benjamin Franklin's 1752 lightning experiments. Later, Nikola Tesla theorized detailed concepts for pulling the high direct voltage potential out of the sky and converting it down into usable low-voltage alternating current. In the 1920s, Finnish inventor Herman Plasson actually built high-altitude collectors, flying large magnesium-aluminum aerostats studded with sharp metallic needles to gather the charge. The resulting equipment was highly unstable, dangerous to operate, and completely impractical for sustained generation. This diagram outlines a modern approach proposed by researchers. By mapping exactly how moisture droplets form and release electrical charges, high-altitude probes gather the ambient energy, transferring it entirely into high-capacity supercapacitors on the ground. Draining charge from the sky at industrial scale removes the electrical potential that regulates the Earth's global electrical circuit. Disrupting this balance would trigger regional climatic shifts, manifesting as intensified thunderstorm activity in some zones and severe, prolonged droughts in others. Extracting atmospheric energy at this scale risks a permanent, unpredictable shift in the planet's climatic stability. Because intermittent sources cannot guarantee supply, engineers are exploring radically different ways to balance the grid. Osmotic power plants utilize the chemical mixing of freshwater and saltwater at river estuaries, generating a pressure differential strong enough to spin a turbine. While chemically brilliant, the pressure generated is minimal. Osmotic generation remains an experimental concept, with only a single operational plant in Norway. This cross-section illustrates a solid-state gravitational system. These facilities are enormous mechanical batteries. When wind turbines overproduce, surplus energy runs a massive motor, slowly raising thousands of tons of weight high into a shaft, storing the electricity as gravitational potential energy. When solar output collapses, the facility drops the heavy weight. As it falls, it forces the motor to spin in reverse, instantly transforming the unit into a generator that pumps the stored electricity directly back into the transmission lines. This relies on the exact same mechanical logic as pumped storage hydroelectric plants. Electricity pumps water up a mountain into a reservoir, holding it there until grid demand requires the water to rush back down through the turbines. These mechanical reservoirs demonstrate that intermittent renewables cannot function without a parallel, massive investment in secondary storage infrastructure. The absolute bottleneck preventing a rapid, global transition to clean energy is our inability to store electricity efficiently. We currently possess no single battery technology that is simultaneously high capacity, capable of rapid discharge, highly scalable, and cheap. This limitation directly challenges the popular concept of distributed generation. The theory suggests that individual households can detach from the central grid, utilizing personal rooftop solar panels or backyard wind turbines to power their own homes, and seamlessly trade their surplus energy with their neighbors. This visualization shows the physical requirement of an electrical network. Alternating current grids demand perfect synchronization. A network only remains stable because it possesses a dominant, centralized generating unit capable of regulating grid frequency and executing an automatic restart during total system failures. If a microgrid of 100 homes, even with 30 independent solar or wind generators, is severed from the main high-voltage substation, the physics immediately collapse. With the heavy central unit gone, none of the individual generators possess the physical mass to establish a reference frequency. The grid frequency will instantly begin to fluctuate. Household solar inverters are highly sensitive components, explicitly designed to operate strictly within a stable frequency. As the waves destabilize, these inverters will automatically trigger their internal protection circuits, aggressively shutting off their own power production to prevent electrical fires. High-voltage transmission lines function because they are deeply engineered with specialized supervisory control systems, precise data acquisition software, and directional protection relays. Local neighborhood distribution networks consist of passive wires, lacking the hardware required to orchestrate independent power flows. Disconnected from the main line, a neighborhood of solar panels will simply instantly shut itself down. The only technical solution capable of allowing distributed generators to operate as a self-sustaining island is the installation of massive central batteries priced at hundreds of thousands of dollars per block, making true autonomous decentralization economically unviable. Small-scale generation functions extremely well, but strictly in a supplementary role. Rooftop solar requires the primary, centralized grid to act as an infinitely sized balancing buffer to absorb its erratic spikes in output. The actual physical limits of electrical engineering dictate a very specific path forward. Securing our energy supply requires abandoning the myth of off-grid decentralization and instead aggressively diversifying the generation sources that feed our centralized networks. This diagram shows the necessity of blending highly varied sources. Injecting wind, solar, geothermal, and rigid nuclear baseload into a unified grid smooths out the severe intermittencies of any single technology, maximizing the resilience of the entire electrical macrosystem. Maintaining electrical stability strictly requires a multi-layered hierarchy. Massive centralized generation pushing raw power into high-voltage transmission lines, stepping down to medium-voltage distribution grids, and finally reaching low-voltage consumption points. The appealing political idealism of total off-grid independence repeatedly collides with the immovable laws of system architecture and frequency synchronization. Managing complex energy states requires immense, highly organized infrastructure. Transitioning our civilization away from conventional fossil fuels is an absolute necessity, but acknowledging the rigid, hierarchical structure required to move that energy is the only framework we have to accurately separate the actual engineering possibilities of alternative generation from the physical impossibilities.